Hello everybody, we're going to talk for the second bonus about shear flow. What is it? Where does it come from? Maybe hand wavy derivation. So normally the symbol used is Q. It represents what I would call the shear force or gluing force per unit length. Okay, so let's call it the gluing force between two shear layers per unit length. You'll find it by using the formula V, which is the shear force you'll get from your shear force diagram, times by Q, which is the first moment of area, where the area you're looking at will typically be looking at things above neutral axis. So the first it'll be the first moment area where you will want to go from the top to the lower position, and that lower position is where you're working out the shear force or the shear flow at that particular location. Talk about that in a minute. And then second divided by second moment of area. Okay, so it's not too clear what I'm talking about for the Q's, so let's draw a diagram for that. So we'll do just a square beam, neutral axis, and I want to find what Q is, let's say at this location here. Okay, so we'll call that Y. Big Q is based upon this area here, so I'll call that A1. Okay, so if we had Y to be the lower section of that area, and I'll call Y top to get to the top of that section. If I was dealing with say a simple square, Q is defined as the integral of Y with respect to area. So for simple shapes like squares, typically you're going to be dealing with squares and rectangles. You can simply find that by how would you find that? You find that by the centroid. So in this case that would be Y plus Y top divided by 2. Right, so that's in effect of your Y there, and you would multiply that by the area of A1. So in this case that's going to give me, I didn't give myself enough space, Y top, take away Y, and then I need to know the width. So normally the symbol given for the width or the breadth of your beam is T. I suppose to kind of represent thickness in the breadth direction. So T, sometimes B, but normally T. So that's straightforward to find what Q is. Okay, so that's your first moment of area. your I is not the second moment of area for this section, but your I is the second moment of area for the entire section. So for this kind of problem here, so we're doing with a square thing, so y top, get from there, t is the width, so we would just go and look up our formula for the I, so b d to the power of 3 over 12. What's the breadth? That's t. What's the depth? That would be, in my case, 2y top to the power of 3 over 12. So that becomes 2, 4, 8, 8 over 12 divided by 4, 2 over 3. Okay, can you just see that? Yeah, you can. So, so that's my expression for the Q, that's my expression for the I, for a nice simple square beam. The V I would find from doing the shear force diagram. I need to do the shear force diagram. So we've got a beam length L. Let's put a force in the middle, P. So the reactions here are going to be P over 2, P over 2. Put it bang in the middle. Your shear force diagram will be therefore P over 2, drop P, move along. So we've got P over 2 here. Okie dokie. So this is your shear force diagram with respect to X. So we can see that we can get a sudden switch in shear flow. So it'll be telling me that it'll be going in one direction, and then I suppose it's going in the opposite direction as we go past the loading. So we've got all our terms there. So we can find the shear flow, okay. Shear flow is shear force per unit length. Well, that doesn't tell me bugger all really. So what is that in real language? Well, force divided by length. So if I take Q and now divide it by T, I'm now going to get shear force divided by area. Force divided by area is stress. So if you take your Q, V Q I, and divide it by, in our case, this thickness here, that will then become the shear stress. Okay, so then that will be actually something useful. Right, so then probably we know how well things, how much shear stress things can maintain, whether they're glued together, or how much shear stress we're going to apply, is being applied between two layers. So what do I mean by that? Okay, so let's we're going back to this beam problem. Let's imagine that the beam is made out of two sections. Ideally we want to do infinite number of sections, and they're all kind of glued together. don't know if you've ever had a what's it called, a millefeuille. So layers and layers and layers and layers. There's a cake with loads of tiny layers on top of one another. So I'm just going to take, imagine we've got two big layers there to demonstrate my point. So when I put the load on, I'm expecting this thing to, the one at the top, to get slightly compressed. And in relationship to the lower one, we'd expect this to maybe get slightly extended. So we'd end up with something like that. Now, in actual fact, we've always assumed that our beams have sort of stayed together and give us a nice smiley face. Like that. So we've assumed that this can't happen, and so for this not to happen, what we need therefore is this shear flow thing. So what the shear flow thing is going to do is basically create a shearing force that will keep this top layer stuck to this bottom layer, so that when I apply the force we end up with this and not this case here. Whoops, that's an unsmiley face. That's a smiley face. Okay. Now if we imagine loads of these things stuck together, what will happen is I can see that at the top this will be moving on like this, and this will be moving a little bit more like that and that, and there's nothing to make the top layer want to stick to anything else. So what I can see then is that the shear stress or the shear force per unit length, the Q at the top, is going to be equal to 0. And it happens that along the neutral axis you'll find that the Q is equal to the maximum at the neutral axis. So coming back to our simple square beam problem, if we wanted to find Q max, we would set Y to be 0. So let's put those values in, see what you get. So you get the shear force value. So your shear force value for this simple problem is going to be P over 2. Okay, so we assume that this flips suddenly. It's either P over 2 or minus P over 2. So I'll put in P over 2 in a minute. The Q, well, I'm taking Y to be 0, so that ends up with Y top over 2 times Y top times T. Actually, what if I times T there? Oh yeah, because it's the area, sorry. Times T divided by I, which is 2/3 T Y top to the power 3. Typically interested in the shear force, so let's find that. So we divide that by T, divide that by T. So what does this give me? It gives me V is 3/4 and I'm going to end up with y top divided by t. Okay, so that tells me my top, and that's the t. So that gives me a different value to what you would expect the shear force to be, which would be V divided by 2y top divided by the breadth, the t. Okay, and in actual fact this value is going to be a bit bigger. Right, so I'll do another video, I think, where I'm going to look at this term and then derive the palabra, and then we'll do a bonus video, bonus 4, on hand wavy derivation for the Q term.